This is a video lesson for conservation of momentum. The learning target for this lesson is, I am learning to describe the behavior of a system using conservation of linear momentum. The success criteria for this lesson are, I can understand that the total momentum of a system is the sum of the momenta of the system's constituent parts. So the total momentum is the momenta, so the momenta added together. I can understand that in the absence of external forces, a change of momentum of an object within a system must be balanced by an equal and opposite change of momentum by another object within the system. So if you have multiple momenta within a system, if you change the momentum of one part, another part within the system has to change in an equal and opposite way. And I can understand that any change to the momentum of a system is due to a transfer of momentum from outside the system. So if the momentum of the entire system changes, that has to be due to a force from outside the system changing the momentum. So momentum can be exchanged. As in the momentum collision lab that we did, when objects collide, momentum from one object is exchanged to the other object. So in other words, delta P1 is equal to minus delta P2. So one object has a change of momentum and the other object has the equal and opposite change of momentum. In an isolated system, where there's no external forces outside the collision, the total momentum change equals 0. So delta P1 plus delta P2 equals 0. So when the change of momentum is the same but opposite, or is equal but opposite, and there's no force outside the collision, the total momentum equals 0. The total momentum change equals 0. So we consider the two masses to be a system in this example. Total momentum of the system equals the momentum of each mass added together. So here we have, before the collision, we have the mass of cart 1 and its initial velocity, v1 naught, and we have the mass of cart 2 and its initial velocity, v2 naught. So the total momentum, the initial total momentum, p tot naught, is equal to the mass of 1, mass 1 times velocity initial 1, plus mass 2 times velocity initial 2. After the collision, we have the velocity of cart 1, and we have velocity of cart 2, so p tot final is equal to mass 1 times velocity 1, plus mass 2 times velocity 2. So this is the final velocities. So the momenta of cart 1 after the collision is mass 1 times v1, and the momentum of cart 2 is mass 2 v2. So when we put all this together, we end up with our conservation of momentum equation. m1 v1 naught plus m2 v2 naught is equal to m1 v1 plus m2 v2. So let's look at kinetic energy and momentum. So kinetic energy is just another way to quantify motion. We've looked at kinetic energy before. So kinetic energy, we use the symbol K. It's measured in joules. It's the energy of organized motion, or the ability to do work through motion. And so when we equate kinetic energy with momentum, kinetic energy is 1/2 mass times velocity squared, and momentum is p squared over 2m. So when we're equating momentum to kinetic energy, we have to square the momentum. So imagine m squared times v squared divided by 2m, so that it's equal to the kinetic energy. So let's talk about different types of collisions. So there are different types of collisions. There's an elastic collision where momentum is conserved and there's no loss of kinetic energy. There's inelastic collisions where momentum is conserved but there's some loss of kinetic energy, often due to heat or sound, some other types of loss of energy. And then there's a perfectly inelastic collision, and this is where objects stick together and have the same final velocity. So in our collision lab, where the two carts came together and were stuck together with Velcro, that would be a perfectly inelastic collision. In our collision lab, where the two carts collided and didn't quite touch because the magnets kept them from touching, that would be an elastic collision. So we're going to look at each type of collision in detail in a later lesson. Okay, so let's look at some examples. So we have a 0.004 kilogram bullet is fired at 940 meters per second into a 2 kilogram block of clay initially at rest. The velocity of the block afterward is 0.5 meters per second. How fast does the bullet leave the block of clay? Note this is an inelastic collision. Some kinetic energy will be lost in this collision. Okay, so let's start with our conservation of momentum equation. So we have m1 v1 naught plus m2 v2 naught is equal to, now this is a inelastic collision, but the block and the bullet don't stick together. So we have m1 v1 plus m2 v2. Okay, so let's plug everything into our equation that we know. So m1 is the mass of the bullet, so 0.004 kilograms times velocity 1 is 940 meters per second. And then our velocity of the block is 0 initially, so we'll just leave that equals to 0. So that's equal, and then the mass of the bullet is 0.004 kilograms. And we don't know this velocity, that's what we're looking for. And that's plus, the mass of the block is 2 kilograms, times, and the velocity is 0.5 meters per second. Okay, so 0.004 kilograms times 940 meters per second is 3.76 kilogram meters per second, and that's equal to 0.004 kilograms times V1 plus 1 kilogram meters per second. So subtract the kilogram meters per second from the right side to the left. We have 2.76 kilogram meters per second. It's equal to 0.004 kilograms times V1. So V1 is equal to 690 meters per second. So the bullet slows down a lot, but it's still going pretty fast once it leaves the block of clay. All right, example number 2, this is an AP question. So a block of mass m is moving to the right with speed 2v toward a block of mass 3m that is moving to the right with speed v as shown. There's negligible friction between the blocks and the horizontal surface they slide on. The blocks eventually collide and stick together. What is the speed of the two-block system immediately after they stick together? All right, so this is an perfectly inelastic collision. So our conservation and momentum equation changes just a little bit for a perfectly inelastic collision. So we have m1 v1 naught plus m2 v2 naught, and that's equal to, so our masses are added together here since they stick together, and then we have a final velocity that's the same. So the final velocity is applied to both the masses together. So let's work on this problem based on that equation. So we have our mass of 1 is just m times 2v. That's plus our mass is, or the second block is 3m times the velocity v. And we have, then we add our masses together. We have m plus 3m, and we're looking for our final velocity. All right, so I'm going to bring all this down here to the side. So we have 2 MV plus 3 MV, so that's going to be 5 MV, and that's equal to 4M times VF. We're solving for VF. So VF is going to equal 5MV divided by 4M. So our M's divide out, and we're left with VF is equal to 5V over 4, which is our answer, choice C. Okay, so what have we learned in this video? So we learned about total momentum. So the total momentum of a system is the sum of the momenta of each of the system's parts. So if there are multiple parts to a system, the momenta of each part of the system added together gives us the total momentum of the system. We learned about the change of momentum. So in the absence of external forces, a change of momentum of one object is equal and opposite to the change of momentum of another object. So if one object changes momentum, as long as there's no other outside forces acting on the system, another object has to change momentum in an equal and opposite way. And we learned about changes to a system's momentum. So this only occurs when there's an outside force applied to the system. All right, thanks everyone.